So this is the third and last week of polynomials. If you didn't like polynomials, you're in luck. This is the last week we're doing it. And yeah, that's basically it. So next week we'll be going into a different topic. So I hope you're excited about that. And since today is Pi Day, here's a nice little pi fact. I think a lot of you might know this, but pi is actually equal to this expression. And it's a really nice pattern, right? Because you plus and minus alternately fractions, and the denominator is literally the odd integers, right? So I just think this is a really cool way to calculate pi, and it's just a nice little pi fact for Pi Day. Unfortunately, we're not doing geometry today. If we were, that would be a lot better, a lot more suiting. We're doing polynomials, and we're probably not going to use pi ever for the rest of today. Okay, so just a quick survey right now. How many of you guys are going to go to Stevenson for high school one day? I just want to get a quick survey here. Chloe's going to go to Stevenson. We got one. So maybe you can do a thumbs up if you're going to go to Stevenson. I want to get a quick survey here. Oh, Jonathan as well. Jenny too. Very cool. So I will see you in math team when I'm a senior probably. And I hope then that'll be a pretty fun time. Okay, so looking forward to that. Let's just get started then with what we're going to do today. Oh, Adrian as well. So I think the majority of us are actually from Stevenson. Very nice. Well, I think I saw some of you yesterday at the math circle meeting. So just happened to ask that question today. So the topics are, we're going to review difference of squares and some difference of cubes. That's really important. I touched on this in week, I think that the first lesson for this semester. We're going to go over Simon's favorite factoring trick. Nice little, we didn't get to that last week. And we're going to do some special factorizations. So basically, it's getting more advanced. Okay, so let's first look at these difference of squares and difference of cubes. The difference of cubes is a little blurry, but these, just keep these in mind while you're doing the lesson today, because we're going to be seeing this quite a bit. So difference of squares, I think most of you should be pretty familiar with this already, but just touch up on your knowledge about difference of cubes, sum of cubes. And yeah, I'll just keep the slide open if you need to write it down. But yeah, so we just need to just keep this in mind while you're doing the problems today, because you're going to see them a lot. Right? Now, Simon's favorite factoring trick. We did not get to this last time. Simon's favorite factoring trick is just a way to factor problems that don't seem like you're able to solve factor. So here we have a sample here. It says, what pairs of positive integers m and n satisfy this equation here? Okay. So let's move everything to one side. So using Simon's favorite factoring trick, we can factor this. Okay. So I like to compare Simon's favorite factoring trick to completing the square. When you're completing the square, you have to add something to be able to make a square, right? You have to insert a number here on both sides so you can turn this side into a perfect square, right? So we got to insert a number on this side, and since it's the equation, we got to do it on the other side as well. We have to insert a number so we can factor this equation. So how will we do that? Well, Simon's favorite factoring trick basically is factoring by grouping. So we're going to factor these individually and factor this and whatever thing we have to add to here. Okay. So we're going to factor these by two groups. So factor the groups individually and then put them together. So if we factor this first group, we get m and minus 5. So to be able to factor by grouping, the other term must also have an n minus 5 inside it. And for that to be true, we got to have a negative 5 in the front because this term is negative 5n. So you do negative 5 times n minus 5. But we don't have this extra 25 in the equation, right? We just basically took that out of thin air. It appeared. We have an extra 5 times 5, 25 on the left side. So we got to put that on the right side as well. And that's how we're going to factor. Now we can factor by grouping. On the left side, we can factor by basically reverse the distributive property, n minus 5, n minus 5. So that's why it was important we had to have n minus 5 here on both of the sections. And this must equal 25. So now it's a lot easier to solve this equation because solve this problem because we want to find what pairs of integers satisfy this equation. Well, for every pairing of n minus 5 and n minus 5, then multiply to 25, we can write those out. 1 and 25, 5 and 5, 25 and 1. For every pair of those, we have an equivalent unique pairing for m and n, right? For this, we have m equals 6 and n equals 30, right? Because m minus 5 would be 1, n minus 5 would be 25. So we would have 11, no, not 11, 10 and 10. And this one we would have 30 and 6. And those are the pairs of positive integers, 6, 30, 30, 10, 10, 10, and 30 and 6. And if you plug that in, you will get, you will see you will have the same answer. So a lot of equations can be solved with Simon's favorite factoring trick. It's basically like completing the square. The idea behind it is you want to add something to the left side to be able to factor it. Okay, because right now I can't factor. You have to force the equation to be able to factor by adding something to both sides because it's an equation, right? So let me actually go over this procedure one more time. So to first factor, you got to get everything on one side. Equals 0. We can't factor this right now because if we group these, you would have m n minus 5. Since we're factoring by grouping here, we have to have another n minus 5 term here, so we can use the distributive property to put them all together at the end, right? So we got to get another n minus 5. But to have n minus 5 here, the coefficient on the n minus 5 has to be negative 5. Otherwise, we wouldn't have a negative 5n. But since we had this negative 5 there, we basically had a positive 25 appear out of nowhere because when we multiply negative 5 and negative 5, we get 25, right? So that's appeared out of nowhere. It doesn't belong in my original equation. So I got to add the 25 to the other side as well. And now we can just factor, and that's basically how we do it. Okay. So any questions here? So I think the best practice you can get out of this is just doing a lot of problems. So let's get into those. So 2 problems here. You may see that these equations don't look like the equation we had in the sample. So you want to alter them so it looks like what you want. Okay. I'll give you guys, these are a little more difficult. Let's do the first one for 5 minutes and then we'll talk about it and then look at the next one. So I think it is suiting to go over one more example before you guys dive in. So when I was learning Simon's favorite factoring trick, it took me so long for it to click. So don't be worried if it's not yet working for you right now. But I like to write it in the form 2ab plus a plus b equals 5. Just to get the a, b on the left. So it seems like we're going to factor by grouping. We're going to factor these, and we're going to factor b with whatever extra constant we're going to add in the end. So if we factor the first group, we take the a out, 2b plus 1. 1. So if we want to factor by grouping, we got to get another 2b plus 1 in there. For the coefficient of the 2b plus 1 term, it has to be a 1/2. Because otherwise, we're not going to get just a b if we multiply 1/2 and 2b, right? So the coefficient we're going to put here depends on how that b comes out, on what the b is actually in the original equation, right? So we multiply by 1/2, so if we expand it out, the 1/2 and the 2 cancel. But we've taken 1/2 and 1. If we do that, we've invented a 1/2 out of nowhere. So we got to add that to the other side. 11 over 2 now. And we just factor by grouping. A plus 1/2, 2b plus 1 equals 11 over 2. Okay, clear some space here. I don't like fractions. They are not very good. So let's multiply both sides by 2. I'm going to multiply this by 2, and I have to multiply this by 2 as well. So if we multiply those by 2, this turns into 2a plus 1. Conveniently, it looks exactly like 2b plus 1, and this multiplied by 2 equals 11. Okay. So now I just got to figure out, since a and b are integers, 2a plus 1, 2b plus 1 are also integers. So I got to figure out what integer pairings can multiply to 11. So the difference between this problem and the last problem was the last problem said positive integers. This one just says integers, which means we've got to consider negatives as well. So either we can have 2a plus 1 equals 1, and then 2b plus 1 equals 11. Or we could have it flipped. 2a plus 1 was 11, and 2b plus 1 is 1. Or we could have 2a plus 1 is negative 1. 2b plus 1 is negative 11, because those pairings also multiply to positive 11. So you got to consider our negatives now. And these two solutions give a equals 0, b equals 5. These two give a equals negative 1, and b equals negative 6. So we got 0, 5, that's a pair, negative 1, negative 6. And if we were to reverse it, it wouldn't really change anything because we're just reversing which is a, which is b. So we've got two other equations. We just flip those two. And those are our 4 pairings. Any questions?
Well, yeah, you talked a bit fast.
Mm-hmm.
How did you get that first equation, 2a plus 1 times 2b plus 1?
Okay, so I'll go back to that. So we start out with just kind of rewriting it so it looks prettier. 2a plus 2ab is in the front. So we're going to factor by grouping here. We're going to group these two together and factor them, and group b and whatever we need to add here together. So if we first group the first two, and we just factor it immediately, we get a 2b plus 1. Factoring those two terms. To factor by grouping, we need another 2b plus 1 term here so we can use the reverse distributive property. So we got to have another 2b plus 1 as a factor. So what's the coefficient on this term? Well, if we want just a regular b term from the original equation, we need to have a 1/2 here so it cancels out the 2, right? So now that we factored it this way, we have an extra term here. We have an extra 1/2 because if we multiply these two, we've got an extra 1/2 that wasn't in the original equation. So we basically added more to the left side. So we got to add that to the other side. So 5 plus 1/2, that's 11 over 2.
Wait, what property did you said you used the inverse property before?
So we used the reverse distributive property. So as you can see here, we got two terms. We can use the reverse distributive property to take a and 1/2 out of that and 2b plus 1 here.
Oh, I don't really know that property.
But it's just the distributive property of reverse. If the derivatives again, it would just be a 2b plus 1 1/2 2b plus 1. Richard, you know the distributive property, right?
Yeah.
Yeah, so that's what we're doing here. We're doing it backwards. Instead of distributing, we're undistributing.
Okay.
Undistributing is basically factoring, right? So that's what we're doing here. All right, all good? Any other questions? And then to make things look easier, I just multiplied both sides by 2 to get rid of the fractions. Just personal preference, and it also makes the final calculation easier as well. Now let's look at the next one. This one's from Mathcounts. Find all positive integers x that there exists an integer y satisfying this fraction equation. The problem here is that you can't use Simon's favorite factoring trick immediately on this equation. You got to manipulate it so that you can use it. So 5 minutes for that one. Okay, so the trick for this one is that we have to use one of those fraction conversions we used in the beginning of the semester. So instead of 1 over x plus 1 over y, we can convert this into x plus y over xy. We have that now, right? Now we can just cross multiply. We get xy equals 7 x plus y. To factor with Simon's favorite factoring trick, we're going to move everything to one side. And I basically distributed that 7. And just factor with Simon's favorite factoring trick. We can factor the first two. X takes out and y minus 7. So if we want to factor by grouping, we've got to have another y minus 7 in the other term. For that coefficient on the y to be negative 7 in the original equation, the coefficient has to be negative 7 here. Okay. But now, if we do negative 7 times negative 7, we get an extra 49. And that extra 49 was not in our original equation, right? So I got to add that to the other side as well. Okay. So now we can factor. All right. So now we can clear up all this stuff. We have a really nice and simple equation here. We basically just want to find the pairings of x minus 7 and y minus 7 that can multiply to 49. Since they're positive integers, these two must also be integers. So the pairings with x minus 7, y minus 7 have x minus 7 equal 1, y minus 7 equals, we could also have x minus 7 equals 7, y minus 7 also equals 7. We could have x minus 7 equals 49, and y minus 7 equals 1. Solving all these, we will have a positive value for y, so we just need to really find what are the x's, right? So the first one gives x equals 8, that's one of them, x equals 14, another one, and finally x equals 56. That's the last one. So we got 3 positive integers x that work, and yep, so we do not have to consider negatives here because everything's restricted to the positive numbers. Any questions? Cool. So 2 more problems here. This one should be, should not take that long. I'll give you guys 7 minutes. Let's just do the first one. So another change here, integers. So the first one should be, so we got to turn this word problem into an equation. So find all pairs of integers for which the sum of the integers is equal to their product. So let's say these integers are x and y. So the sum has to be equal to the product, which means xy equals x plus y. This looks like an equation we can factor using Simon's favorite factoring trick. Let's move everything to one side first. Now I can factor this first group. We gotta have another y minus 1 here, so. But to have that y minus 1 exist, the coefficient on the y has to be -1. So we gotta put a -1 here. But look, we've added a 1 into our left side, so we gotta add the 1 to the other side. So we get x minus 1, y minus 1 equals 1. So what pairings work? Well, x minus 1 equals 1, y minus 1 equals 1, or x minus 1 equals -1, and y minus 1 equals -1. And these give 2, 2, 0, 0. Okay. So from inspection, those, if you go back and check those, they should look pretty obvious to you. But those are actually the only two pairings of integers that can do that. So that's how we can show that there's not any more solutions there. At least in terms of integers. There are lots of solutions if you don't include integers. Okay. Now I'm going to skip ahead to these special factorizations here. So if we remember the sum and difference of cubes, here are some more general cases of those formulas. If we have any integer n with the difference of powers here, just like difference of cubes, n was 3, right? If we have any difference of powers here, we can factor it as x minus y, take that out, and then we're adding a bunch of these terms together. And what do these terms mean? They basically mean, so let me just write this out. This formula is general. So let's say if n was 5, for example, x5 minus y5, we can factor this as x minus y, and then following the formula here, it's basically just x to the 4th plus x to the 3rd y plus x squared y squared plus x y cubed plus y to the 4th. And that's how you would factor it. Okay. So what this basically is that we have a bunch of, so we start out with the greatest power of x, and then x goes down by increments of 1, and y goes up by increments of 1, basically. And that is how we would factor it, actually. If you look at the difference of cubes, that is just a special case of this formula. X cubed minus y cubed, what was that? That was x minus y, and x squared, plus xy plus y squared. It's just a special case of this formula. And if you're not convinced that this is true, you can just literally just multiply it out, and you can see that a bunch of the terms will cancel which will leave only x to the fifth minus y to the fifth. And this works for any integer n. So if it was x to the fourth, for example, you can also factor this one in the same exact way. Right? So that's basically this first formula. The second formula only applies to odd integers. So if we have an odd integer, we can have the same thing with the sum. If n is odd, then we can use this formula, where we have the sum and we can factor it like this. But if you look here, instead of having all pluses, this formula has a minus, a plus, a minus, plus, minus, plus, minus. It alternates, just like when we did Vieira's formulas, it's kind of like that. It alternates, and it always ends in the plus. Because it works out that way, because n has to be odd, which basically limits the number of terms we have to be an odd number. And that's why we have a plus at the beginning, plus at the end. We alternate plus minuses in the middle. And that's this formula. So special case, sum of cubes. This will factor as x plus y. And then we've just applied this formula. It's basically this, but we're just alternating plus minuses. Okay, so we're going to do x squared, a minus xy, and then we're going to do plus y squared. And that's it. We can do this for x to the fifth, y to the fifth. Another example here. We can factor this as x plus y, x plus 5, x plus y. And we start out with positive and we alternate. And it works just like this one. So we're going to do x to the fifth minus x to the fourth y plus x to the third y squared minus x squared y to the third plus xy4 minus oh wait, you had to start out with a 4 here. Start out with a 4. So the first one is x to the n minus 1, because otherwise you would get an x to the sixth power, right? When I did this as 5, what happened was if we were to multiply these, we would have an x to the sixth power, which is not here. So really careful about that. We had to start out with a 4 first. And that's the factorization for x to the fifth plus y to the fifth. And these are very, very helpful formulas that you can use. So one question is, why can't this last formula apply for even integers? Why can't that work? Any ideas here? Well, do you have a formula for x squared plus y squared? Is there a formula you can use to factor that? We don't. Why not? Well, if we were to set this equal to 0, we would have x squared equals negative y squared. But obviously that can't work, right? Because if we have anything to an even power, they have to be positive. So if, let's say x was positive, x squared was positive, then negative y squared's got to be negative. Right? So x squared and y squared would be opposing signs if this was true, which would only work with imaginary numbers, which is beyond the scope of this course, but it would work with imaginary numbers, but it's not going to work here. Because basically everything has to be the positive. This has to be positive, this has to be positive. So we can't have a negative number, can't have a negative here. Okay, so that's why this formula, last formula, doesn't work for even integers, but it does for odds. Okay. Any questions? These are just some special factorizations. You can verify that these are true by multiplying both sides, expanding it. It's a pretty easy verification, but just it requires a bit of work. So you can do that on your own time if you would want. Here's some problems here. Let's factor these 3 equations. All right, really good job, guys. I can see you've been chatting your answers. Those probably took a while to type. Yeah, so thank you for replying, but I don't think it was absolutely necessary because we're just literally just polynomials. It's going to take forever to type. But for the first one, it's just difference of cubes. That's it. Second one, the two ways we can do it. We can first apply the special factorization formula we learned earlier. Got to factor this. This we can factor by grouping. These can factor, these can factor. Okay, so then we got x squared plus y squared. Y. Got to take this back here. Oh, where's my y? Oh God. There's no y. Y is 1. Okay, just imagine those y's are 1. Okay. And the other way we could do it is the difference of squares. A lot easier actually. X squared minus 1 plus 1. This can factor more. Right, that one was pretty simple. Now the last one, x to the 5th minus 1. You just apply that formula we learned. And that's basically as much we can factor. Okay. Last one's basically very similar, except one we have 32. Wait, I wrote the one. I wrote the y's in there again. So this one would be x minus 2. Basically x to the 4th plus x to the cube times 2. X squared times 2 squared. X to the cubed times x to the 1. To the 3rd. And if you were to simplify that, that would be your answer. All good on these? Some more advanced ones now. These look a little more scary. So I promise these are manageable with the formulas you've learned. So give you guys until, sorry, class a little late, so I'll give you guys 5 minutes. So my hint to you is you can use those factorization formulas in reverse. That's the hint. Richard, please don't chat it to everyone. Yeah, if you're trying to chat it to
that to be private.
What?
I meant for that to be private.
Yeah, that's okay. Just make sure you're chatting it privately. And Richard, can you check your answer there? If you expand it, it does not get you to, if you were to like do it the other way, it's not going to get you to the actual answer. So check your answer right there. first one, it doesn't look like anything we've had because all the formulas we have, it's kind of like they go in order, right? If we were to have like x to the fourth minus 1, if we were to factor this, it would be x minus 1. It would go down, the powers would go down by increments of 1, right? Remember, this is how you would factor it, go by increments of 1. These go down by increments of 2. So we can't directly apply our formulas here. So how do we make them so they actually will go down by increments of 1? And the trick here is that we substitute y, some kind of y variable, in as x squared. If we put y in here, observe what happens. I don't know about you, but this looks suspiciously like x cubed minus 1. Remember x cubed minus 1? Oh no, y cubed minus 1. It's got to be a y. Over y minus 1. Because difference of cubes, remember? Y cubed minus 1 is just y minus 1 times this. So we can literally turn that in reverse into this. Now I can plug x back in here. X to the 6 minus 1 over x squared minus 1. Now by difference of squares on the top and bottom, we have x cubed minus 1, x cubed plus 1 over x minus 1, x plus 1. Sum and difference of cubes on the top. This gives us x minus 1, x cubed, not x cubed, x squared, x plus 1, and then x plus 1, x squared minus x plus 1. And a little cramped here, x minus 1, x plus 1. Oh, conveniently, these are actually going to cancel out. So we got x squared plus x plus 1 times x squared minus x plus 1. And that is the factorization. Okay. Next one, very similar, to get the answer. This is basically part of the factorization of x6 minus 1, right? x6 minus 1 is x minus 1 times x to the 5th plus x to the 4th. This was from our one of those special formulas. So this is obviously here. So this is basically x to the 6 minus 1 over x minus 1. Okay. You can basically do the same exact thing we did last time. Sum and difference of squares first. Downward, x minus 1, x squared plus x plus 1, x plus 1, x squared minus x plus 1, all over x minus 1. These cancel, and this is our factorization. Any questions here? All right. Well, that is it for today. No more polynomials. If you do not like polynomials, you're in luck. Happy day for you. But other than that, if you have any other questions, stay back. Otherwise, have a good week. All right. Bye, guys.